Thank you very much. Thank you very much, Kara. So I think I'm going to skip the bit where the speaker thanks the organizers for the invitation, right? Let's to be completely honest. Manolis Tiakakis, a very talented experimentalist from Jülich, has been invited, and he was supposed to have a slot. He could not come at the end of the day. So what I'm going to do is I'm going to talk a little bit about things that I am doing, and they touch upon also experimental work that Manolis can do. Here is we switch a little bit gears from the previous session. We're going to talk about topological polymers in the next talk. So what I'm going to do, I'm going to first convince you that topology in polymers matters, starting from neutral polymers, ring polymers, which is the simplest topologically non-trivial polymer. And then at the second part and the biggest part of the talk, I'm of course going to go into the effects that we have if we combine topology and electric charge. And the topic that is central to my talk is threading. So here are two ring polymers, the white and the red one. And I have tried to sketch how the red one is actively threading the white one. Okay, so you're having the red one going through the surface that is spanned by the white one. So when I'm talking about threadings in the talk, this is what I am going to mean. All right. So first of all, let's talk about individual, and always in red are the names of the people who have collaborated. So let's start with the basics. We want to know how self-avoiding ring polymers scale, how they size scales with the degree of polymerization. And it's no surprise it has exactly the same self-avoiding exponent as linear polymers do. As a matter of fact, ring polymers that are ideal but that cannot cross themselves also scale with a self-avoiding exponent. So essentially, there are no ring polymers that have exponent 1/2. And we can also look at an object which is very important. What follows is so-called minimal surface. This is the surface that you span, ending at the ring polymer and having the lowest surface. And this also scales with an exponent which is about twice the exponent that you see. Okay, so this is by taking samples of very, very long ring polymers reaching lengths up to, as you see here, up to 10,000 monomers. Although for most of my talk, the polymers are going to be shorter. So then we can ask the question, what is the effective interaction potential between the centers of mass of two such ring polymers, which can be calculated by Monte Carlo methods? And this is a collection of pairs of polymers of different degrees of polymerization from 50 to 3,200. And you see as n grows, the effective interaction reaches some kind of universal scaling limit, scaled over R over Rg. And it has one peculiarity. Well, it has two differences with respect to the effective interaction between linear polymers. First of all, the one between linear polymers is weaker. It reaches about 2 kBt for full center of mass overlap. This one is stronger, it's about 5 kBt. And more importantly, this interaction has a very flat part for distances up to 0.5 the gyration radius, meaning beyond a certain degree of penetration between the two rings, and threading is the dominant configuration for short distances, beyond a certain degree of penetration, you can push the ring even deeper without exerting any force. That's something very peculiar that has to do with the topology of the polymers. The second topological, well, within this potential lies hidden another important topological contribution, namely, in doing the simulation, you restrict the rings not to catenate. So if they were uncatenated in the first place and you let the centers of mass move, they cannot suddenly catenate with each other. Catenates are a topic of the next talk, by the way. And so there is a repulsion that arises out of no interactions between monomers at all. It arises merely because of the fact that catenated configurations are forbidden, and this repulsion is called the pure topological potential, and here I have drawn its shape for various distances. You see that out of this 5 kBt, about 0.5 kBt are of purely topological origin. So topology matters in that sense. Let me skip a few things that are maybe not so important. What I want to focus is the following now. We said that for close separations between the centers of mass, I reach a barrier, a free energy barrier. It's an entropy. All of this is entropy. I reach an entropic barrier which is about 5 kBt, and now in a simulation we can do a very nice trick. We can span a minimal surface on, say, the white ring, and we can say any configuration in which the red ring crosses that minimal surface is artificially forbidden. So we can artificially go and say, don't thread. So try to bring your center of mass close, but not thread. If you do that, your effective interaction shoots from 5 to 12 kb. So most of the configurations, therefore, at close separation are the ones in which the two polymers are threading each other. And these threadings are crucial for a number of purposes. They are crucial for the emergence of what is called sometimes the topological glass in ring melts. They are crucial for the emergence of what I'm going to show in a moment called the cluster glass. And so it's a theme that is going to go through the whole talk. Okay. So up to now, these have been flexible rings, so Kramer-Kress rings with short range repulsion and Feynman bonds between them. So now let's make one further step. We add rigidity, we add bending rigidity to the rings. This is motivated by the fact that there are minirings in nature. There is mitochondrial DNA that has charge. Charge will be added as we proceed. So having an eye on experimental realizations, we said, okay, let's take those rings now and add some bending rigidity. And actually don't make them terribly big. These are rings that have such a bending rigidity that the persistence length is 1/4, say, of the contour length. Okay, they have 50 beads each. So we have added this bending potential. And now I just want to show you directly the results from a simulation that we did with Angel Moreno and collaborators, Angel Moreno and collaborators in San Sebastian, in which such a system was simulated under high concentration conditions. So let me guide you a bit through it. On the left, we have a monomer resolved snapshot, and there we have applied certain proximity criteria, proximity in distance between the centers of mass and proximity in the orientation to identify clusters. So each color characterizes a cluster. Within each cluster, you are having a collection of rings which are lying almost on top of each other, a bit shifted, but with their orientations essentially parallel to each other. And on top of it, something that you may be able to see, for instance, in this cluster or in this cluster, or in this cluster, a few rings that instead of being oblate and stacked, they become prolate, stretch, and go through now the axis of this cluster, further mechanically stabilizing those clusters. And this art of self-organization is purely on entropic, purely on excluded volume grounds. There are no other interactions between the beads. Now, the clusters, as you see, are amorphous. There is no kind of columnar order or the like. Here, by the way, you see clearly that prolate ring piercing through the cluster of oblate rings. So on the right side, you see exactly the same configuration, but now only the centers of mass of those rings are marked. Therefore, you see the formation of these strings and this organization in clusters. Okay. So now let's see what kind of structural and dynamical characteristics this self-organized system has. So let me leave the G of R on away. This is now the structure factor, the S of Q, between the centers of mass of those rings, which has a couple of peculiar characteristics. Well, we start from the lowest density, which is the yellow color, and we increase the density going from yellow to black. And now if we had to deal with the usual liquid, what we would find is that as you increase the density, the position of the peak of the structure factor scales, so it shifts according to density to some power, -1/3. So this happens for a while, but beyond a certain density, which is about this one, 12 in these units, the peak of the structure factor, the position of the peak, which is given by the blue lines, is not depending on the density anymore. You see that the position of the peak does not move anymore, although I am concentrating the system. Moreover, on the other hand, the height of that peak grows enormously. This is a logarithmic scale, so it has reached a value of about 20. And if you come from a colloidal background, you may have in mind the Hansen-Verlet criterion telling you that any colloidal system where the peak of the structure factor exceeds the value 3 is crystalline. This is not crystalline. This system is amorphous. I will argue in a moment that it is glassy, and it has this peculiarity. It has extremely high structural peaks that are independent of how you compress the system. And this independence has to do with clustering. When you form clusters, you are able to maintain the cluster-cluster distance at a fixed position just by putting more and more particles on your cluster. So that is a particular kind of amorphous cluster system, which apart from the structural characteristics that are unusual, has also unusual dynamical characteristics. This looks like a mess, so let me guide you through what is shown here. I mean, most of you know, or all of you know, the coherent and incoherent intermediate scattering function of a concentrated system. So essentially, they tell you the following. Suppose you take your system and you make a density modulation with a wave number q, then you want to know a time t later how much of this is still in the system, how much the system remembers that it has been modulated. Ergodic liquids very quickly forget that. So this function relaxes pretty fast. Glasses don't, so they have these big relaxations. The thing is now you can do this both at the collective level, in the coherent level, where you sum over particle positions j and k being in general different from each other, or you can do it on an incoherent level, on a single particle position, in which you say, well, my particle, a particular particle, how much does it remember a time t later where it has been a time t before? And in usual glassy systems, the two decay together. The celebrated mode coupling theory of the glass transition, for instance, it allows in principle the theoretical possibility that these two decay at different scales. But you don't see it in colloidal systems, because in colloidal systems, glassy behavior arises out of caging. So collective and self modes relax together, because when a particle escapes the cage, then also the cage is destroyed and has relaxed. So these two correlators decay at the same time scale. Not here. Here, you can see a color match at a given density and at the peak of the structure factor. If the density, excuse me, let me go here. At a given Q and for different densities, at the lowest density, where the structure factor was still normal, the self, continuous line, and the collective points, correlation function decay together. But as I increase the density and I form the cluster, the self-correlation function decays much faster than the collective one. The reason being, individually the particles hop from one cluster to the other. So a particle may have forgotten after a few hops where it was, but the clusters as a scaffold, as a structure, are much more longer lived than the individual particles are. So this is what we call a cluster class. Okay, so I skip this one. And now we enter the charge and the importance that charge has. And you would have anticipated that charge should come, because I mentioned DNA minirings, and DNA carries charge. So one of the questions we asked for with Roman when he started his PhD and with Jan Smrek is, how much is this phenomenon affected if my rings are charged? And you would think, well, if you put charge, things repel each other strongly. I don't think that clusters should form, and so on and so forth. But that's not the case. The phenomenon is robust. So let me guide you through the way Roman plots things. Now, instead of showing the whole microscopic configuration of the centers of mass, what we do is we take the center of mass of every ring, we do an eigenvalue analysis of the gyration tensor, and we plot with an arrow the direction of the eigenvector that corresponds to the smallest eigenvalue. Why we do that? Because those rings are small, they usually take a planar configuration, so if you plot that arrow points essentially perpendicular to that ring. And so what you can see, these are n equal 50 rings with monovalent counterions, right? And now we look at them at two different densities. On the left, the density is 0.4 in the monomeric units. On the right is 0.5, we are already at high densities. And you see on the left, there is crowding, there is organization in clusters, there are lines, so to speak, with the arrows pointing for a big part of the line in the same direction. You see it here, you see it there, and there are gaps in between. So this is a cluster phase, as it used to be for the neutral system. However, if you go to the higher density, the system looks much more homogeneous. So preliminary message, crowding here, first of all, creates the glass, but further crowding melts it for reasons that we're going to discuss. Let us look now in the case, I'm sorry, did I skip one? Well, this is a mixture of trivalent and monovalent counterions, and here I increase the density and the clustering remains. The same is true if now we have a fully trivalent counterions, so there's a very strong cluster phase at the lower and at the higher density as well. So the clustered glass remains. Let me convince you that it is indeed a clustered glass. The static structure factor, monovalent, mixture mono, tri, and trivalent. Let's look at the monovalent ones. I'm sorry for the small lettering, but I'm going to guide you through it. So the density grows from red to green to light blue. And so we have the behavior we saw before. The peak grows, clusters form. But then if you reach density 0.4, it stops growing any further. And at 0.5, which is this violet line, it has become a normal liquid again. This is the melting of the clusters in the presence of monovalent counterions. On the other hand, if you have the mixture of mono and trivalent, the clusters survive. And you have only trivalent, you can see that at the lowest density, you even have a liquid-gas coexistence. I mean, the attraction induced by the trivalent counterions is so strong that the system macrophase separates, and then the dense phase forms this cluster. Let's look at our correlators to ascertain that the system has the same dynamical behavior as the neutral one. And indeed, you can take any of these. Let's take the middle one. At the lowest density, the self and the collective decay together. And as you increase the density, you go toward the violet one, they have separated. Only in the case of the monovalent counterions, the gap between lines and points of the same color grows as you increase the density. And then at the highest density, which is this violet color, they are getting back together again. So you have a glass melting due to concentration. So we wanted to understand a little bit, at least on the basis of the simulation results, why this is happening. And let us not forget, these are not colloidal particles, these are polymers. And although they have a bending rigidity, they are deformable. So we know, of course, from flexible rings and from flexible polymers that beyond the overlap concentration, they shrink. These ones are more rigid and small, but they still undergo deformations. So let us take here a two-dimensional plot in which we make a histogram of two things, the gyration radius as well as the prolateness of the individual ring in the concentrated system. Why the prolateness? Because the default shape, so the zero concentration shape of those rings is oblate, right? It looks like a disk. And indeed, at densities that are 0.4 in all cases, it is, the letter is small. So monovalent, trivalent mixture of monovalent and trivalent. There is just essentially a single peak at a gyration radius of 7 in this particular case, and the thing is oblate. It's minus 0.25, 1, 2, 3. Now let's go to the next density, for which the monovalent counterion system starts to melt. And you see here, the other two have maintained the shape. Here, something has happened. Instead of having all the rings in this conformation, you suddenly have oblates as before. You have a bunch of oblates that are much smaller, and a bunch of prolates up here with a very broad size and shape distribution. So what is happening here is that due to the presence of the monovalent counterions, which do not glue, they have a lot of entropy, they don't glue close to the rings. What is happening is the osmotic pressure, if you concentrate the system, crumples the rings. It deforms a sufficient fraction of them. They become either prolate and twisted, or they become oblate but very small. This way, there is another way to accommodate the crowding. Each molecule is now smaller, and it starts behaving like a normal liquid. So you have melting induced by the counterions, melting which is due to the charge, but only with this particular kind of counterions. The trivalent counterions instead, they enhance the glass formation because they act as bridges, as glues between the rings in those stacks. And they even produce stronger glasses than the monovalent counterions do. They are even stronger than the neutral rings. Okay. So that was the first part about the charge rings. Now let me switch topics, but there is a connection at the end. So instead now of looking at rings, I'm going to look at ribbons. So like DNA, I'm going to look at polymers which have a width, all right? So that, we can make Möbius bands out of this. I'm going to make something more than a Möbius band. So if I have a ribbon and I want to connect its two ends, I now have another option. I may ask myself, how many times do I twist this end? So I'm going to twist it a few times, right? before I connect it and I topologically trap this. Let me twist even more. And I trap this tension, this stress I put into the system, I trap it now here. Okay. So here's now my twisted ring, and there are at least two extreme things that I can do. See, I can keep it like this, and you can see that the line, the center line, let's say, of this ribbon is not crossing itself. The center line is an open ring, but the ring has a lot of twist. So if you look at how many times this edge is winding around the other edge, you have a big number. What macroscopic ribbons do instead, they relax like that. If you look now at this curve, it has two crossings, and it has reduced the twist. This conformation is called writhe. W-R-I-T-H-E. I didn't know the word myself. I found out. So here's the idea. So the work that we did, again, with Roman, Davide, Micheletto, and Jan, inspired by supercoiled DNA. So we take ribbon-like polymers, and we put by hand supercoiling on them. All right. By the way, the writhe is what used to happen to our telephone cords. When some of us, well, some of you don't know what a telephone is, and a cord, fine. Those of us who know, remember. Okay, so the stresses, therefore, can be accommodated either via twist or via the writhe. There is a beautiful, a remarkable theorem due to White, Fuller, and Kalugareanu, saying that the sum of the two is constant. It is the linking number. It is the amount of turns I made when I started creating that ring. So you can convert writhe to twist, but the sum of the two has to remain fixed. And it's a fascinating theorem. Oh, I even put down, it's a bit hidden, I put down the journal in which you don't see the most important thing. I guess. No, you still don't see. I find it fascinating that the journal survived the country. Parenthesis, it's a shame Czechoslovakia doesn't exist. It's the coolest name of a country I know. Anyway, so, all right. Huh? Okay, so, right. So the idea is now the following. Can we manipulate, can we induce writhe to twist changes on a single ribbon, first of all, on a single ribbon, by inducing charge via pH modulation. Okay. The motivation behind this, beyond this being, in my view, just an interesting question, is the following. You may imagine having a ring polymer melt that has possibly a few of those manipulable things dissolved in there as well. Now, the rest of your system is just the usual flexible neutral polymer melt. The ring polymer melt is not glassy because the threadings that you have in a ring polymer melt are shallow and retractable, so the thing flows. However, if you could put a few of those clamps inside there, and if you were able to change, let's say, the conformation of these clamps from this to that by charge, then you may be able to you make some of those topological threadings tight. And then maybe, that's still something for the future, maybe you can create a percolating network in which those things act as traps and have a pH-controlled topological glass to liquid transition. I'm not claiming we showed that. This is the goal. So we start from a single molecule, right? So here is a model. For some reason, I cannot flip anymore, but I don't mind. I'll do it this way. So I can't even flip this one. Oh, this whole thing has died. No, it hasn't. Now, so the model is expanded with respect to the previous ones in the sense that the monomers that now Roman is using, they have patches of them. And the patches allow you to see whether a monomer is aligned dihedrally with its neighbor, right? So you can tilt the neighbor, you can tilt the next one, you can put supercoiling in it. So first of all, there is supercoiling. Of course, there is charge. And on top of it, the simulation is enriched by the technique that Steffi told us about on Tuesday, by the constant pH Monte Carlo steps. So you run a number of molecular dynamic steps, then you do a number of Monte Carlo steps in which you do what? You either create a negative charge on a neutral monomer and you put a counterion in the solution, or you eliminate the charge on a randomly chosen monomer and you kill also its counterion. Okay. And as you will see, this way you create fluctuating charges on this weak polyelectrolyte, and in fact, the kind of charge you induce depends on the topological state of the polymer. So let's go through it. First of all, to convince you that the technique does what it should do, the charge per monomer that you induce via pH changes on your polymer is a fluctuating quantity. This is a weak polyelectrolyte. It's not like you fix the charge all over the place. And the reason why this is important is, you will see in a moment, in a writhe configuration, charges do not occur with the same probability independent of the position. At the places where you have close contacts in the writhe configuration, it's not very profitable to create charges. It costs a lot of energy. The technique is powerful enough to be able to capture this. And so indeed, as you increase the delta pH, first of all, you create more charge. This is a fully charged molecule here. It is charged per monomer, and it is also fluctuating with time. So it's doing what it should do. This has effects, we'll see in a moment, on the shape of on the size of the molecule. So now, this is the degree of supercoiling we put in. This is the percent means per monomer. Remember, we have 200 monomers. So at 2%, supercoiling means we put an angle 4 pi, essentially. And the supercoiling varies from 0 to 2%. So a common thing in all of those molecules is that as you change the delta pH, therefore, as you charge the molecule, they swell. Starting from, well, all of them. And we'll see why in a moment. Just to convince you that it's not just swelling, I'm just showing the prolateness and the anisotropy. All morphological characteristics of the molecules realize, oh, the pH has changed, and they realize it rather significantly, right? They are visible changes. All right. So here's a summary of the results. Let's walk through them. First of all, on the left, this is the charge that is induced on the polymer as a function of delta pH, color-coded with respect to the supercoiling you had put in. That would be the ideal curve that ignores correlations. Forget that. These are the real results. You see that the charge that you induce is not particularly sensitive, well, not spectacularly sensitive on the supercoiling, yet there is a consistent trend. The more supercoiling you have, the more difficult it is to charge the molecule. The reason being, if you are very supercoiled, your neutral conformation of the polymer is writhe. And writhe doesn't like charge. This is the area, well, it's related to the gyration radius, so of course it grows. And on the right side, we see now the writhe that the molecule has. This is red on the left axis, okay, and with the continuous curves, and the twist that it has, this you can read on the right axis and with the broken curves. And indeed, as you charge the molecule, writhe becomes smaller in absolute terms. It is signed, it's negative here, but that's not. So writhe becomes smaller and twist becomes bigger. We convert writhe to twist by charging the molecule, and you can see the conformational changes in the snapshot shown here. It's for 1% over 1% linking number. And this is the 2%. Here you see that even at the highest charge, you don't get a completely open configuration full of twists, but you get some kind of domain coexistence. Hara, how much time do I have? 5 minutes. 5 minutes, thank you very much. I think I can finish. So here we have a domain coexistence. This thing is not just global, it's local. If you follow the path along your polymer, here's the polymer underneath, you can see that, I'll flash this quickly because of time, you can see that at the regions where you have locally high charge, remember this is the sign, where you locally have high charge, at those regions you have local twist and no writhe. And this is what you get if you increase the salt concentration. Let me quickly then tell you, because I like this particularly, you can capture all this by a simple Landau theory. So this is a Landau theory having two parameters. Phi is the charge density, W is the writhe density, and W naught is the built-in topological linking number. Well, it's a proxy for that. Now, if you want to see the structure of this theory, first of all, forget the terms with a writhe. So forget that, and that term. Look at the Landau free energy for the charge. It's just a 2-4 Landau free energy with a chemical potential. What's the chemical potential? It's a proxy for delta pH. Moreover, we're not using criticalities here. No, I mean, I'm not going to change the sign of this coefficient. For zero chemical potential, the thing is uncharged, and then if you increase the chemical potential, your parabola tilts and you get more charge. So far, so good. Look at the other terms. Forget the charge, look at the writhe. What these two would do, well, in the absence of charge, when phi is 0, they would just writhe the molecule at W naught. So neutral molecules have a writhe W naught, which is the whole linking number. And the crucial thing is the coupling between the two. And this is the minimal model you can write respecting the symmetries of the problem. Please note that whereas the charge has a chemical potential, the writhe does not. Writhe is not a conserved quantity, right? It's like a photon gas. There is no chemical potential for photons. You get so many created that, as the equilibrium says. And, well, first of all, the theory does for the charge versus pH difference exactly this. Well, it does the thing that simulation does. The charge grows faster for small W naught, for small overcoiling, supercoiling, and less for high supercoiling. And now let me just show you the phase diagram that you obtain by minimizing free energy and so on and so forth. So this is the supercoiling, and this is the delta pH. At low degrees of supercoiling, ABC, green, blue, and purple, you see that what is happening is that as you charge the molecule, what happens to the optimal writhe? It starts at 0.1, and then it just moves continuously to smaller values as you charge the molecule, but without going through any coexistence. On the other hand, if you have a high degree of supercoiling, your free energy goes through a place where it has two equal minima. The locus of equal minima is a line in between those two colored regions. In this region, one of the minima with a more writhe is deeper. In the other region, the minimum with a more twist is deeper. And you have a full coexistence line in between, terminating at a critical point, which captures the physics that we saw in the simulation. All right. So to summarize, so what do we want to go from here? For the first part, for the cluster glasses, and there comes Manolis again, our goal, well, we're working on it, is to look at experimental realizations of this charged cluster glass. Manolis has the systems. Would be nice if we'd been here. For the second part, I just told you that we want to use those as twists to arrest, as it were, deep threadings within ring polymer systems. And on that count, may I call your attention to an alternative strategy developed by Roman, Jan, and then Renata and Dusan from Bratislava, in which instead of using pH, they are having gyrates, and they are putting acting torques on some of those molecules, this way trapping the others and doing viscosity modification. This thing is on archive. I thank all the collaborators, the agencies that gave the money, and you for your attention.